Welcome to T3 Day 1 of Calculus. Today's a huge day because we get to start talking about integrals. So let's talk about this chart, which gives us time and the position of an object. Recall that the derivative, which is the instantaneous rate of change, which is also the slope of the tangent line. And in terms of notation, we're going to have s of t is distance, s prime of t is velocity, also called v of t, and s double prime is v of prime, which is acceleration. Basically, it means the derivative of position is velocity, and the derivative of velocity is acceleration. So let's say we had this table right here, and we wanted to find the velocity at time equals 2. So at this instant right here, what's the velocity of this car? We can do this a couple ways, and the way we're going to do it right now is we're going to find what's the velocity from 1 to 2, what's the velocity from 2 to 3, and then average them. That's one way to do it. So one way to do it is to say, okay, so velocity is going to be change of position over time. So from 1 to 2, it's going to be change of position will be 25 minus 10 over 2 minus 1, and that's going to be 15. And then if you go from 2 to 3 and do the same thing, you're going to 45 minus 25 over 3 minus 2, which is 20. And what you can do is average those two numbers, 15 plus 20 over 2, and you end up with 17.5. Another way to come up with an estimate, would be to just go forward and take 20, or to go from 1 directly to 3. 1 directly to 3, so it would be like 45 minus 10 over 3 minus 1, which would be, in this case, 35 over 2, which is actually the same thing. It's not always going to be the same thing, but there's two ways, and in this case, our best guess is that average that we did first, the average of 15 and 20, to get 17.5. So we just had a table giving us the position of a car. Now, what can we do if we have the acceleration table? The velocity table. The table with the velocity right here. Well, we're going to find out how far the car travels. We're going to make an estimate again because we don't know exactly. We only have data points because a lot can happen between 0 and 1, and between 1 and 2 and 2 and 3 and 3 and 4. So we're going to make a lower estimate and an upper estimate. So we know that from 0 to 1, at time 0, the car is going 20 feet per second, and at time 1, the car is going 30 feet per second. So we don't really know what happens in between 20 and 30, but for a lower estimate, let's just assume in the first second, for almost the entire time, let's say it's going 20 feet per second. Let's assume it's going 20 feet per second, the lowest possible. And how long is it going 20 feet per second? About 1 second. So it's going to go about 20 feet. So in the second second, we're going to do something similar. We're going to assume the lower, which is 30, and it's going to go from 2 to 1, so it's 1 again. And then the third and the fourth. So the third is going to be 38, and it's 1 second again. And then 44, and then 1 second again. So we're assuming the lower estimates here, And when you add this all up, again, it's 1 second, so the multiplication is nice and straightforward. When you add this up, you end up with 132 feet as our lower estimate. Well, if we do the upper estimate, let's assume he accelerates, or this person, or whoever it is, accelerates really quickly from time equals 0 and gets all the way up to 30 feet per second almost immediately. So let's do the upper one. Let's do the upper estimate. The upper estimate would be assuming that they accelerate almost immediately to 30. So for the first second, it'll be 30. So the first second in this case will be 30, and again times 1. And then it'll be 38 times 1 for the second, and the third will be 44 times 1, and the fourth, will be, so that was the third, and the fourth will be 48. So we're assuming the acceleration happens as quickly as possible. So again, we have easy multiplication because the time interval is 1, and it's going to be a constant, or pretty common that this time interval is going to be constant. So that's going to be 48, and when you add this together, you end up with 160 feet. So an lower estimate would be 132, and a upper estimate would be 160. So what we could do is we could average the two, and we could say maybe 132 plus 160 as our guess, because we don't know, and we end up with 146. All we know is that the distance traveled is going to be between 132 and 160 feet. So what does this look like graphically? Well, here's the same data table we were just working with. Again, it's velocity and time. It starts at 20, gets to 30. so forth like this. Now we don't know what it looks like in between. It could go crazy, right? You don't really know, right? But let's say it was a minimum. So the minimum thing we drew was this. We did that first one, which was 20 times 1. And then our second one was, for the second was 30 times 1. And then we went over to here, and it was, what, 38? Yep, 38. So there's our minimum right there. This one's straight over like this. And there it's like this, and then it stops. So we added that all together, and that was the minimum, and that was 132, I think. I think it was 132, yeah. So what was the maximum? The maximum was, we assumed it was 30 the entire time, so it's this whole one up here, and then here, and then here, and then here. And that max was 160. So visually what we're doing is we're adding up lots of rectangles. You are going to add up so many rectangles, so many rectangles. So in terms of some notation, it's important for you to know there are 4 intervals here. So there's 1 rectangle, 2, 3, 4. So we're going to say our n value is 4. That's going to be really common. You're going to break this interval from 0 to 4, from 0 to 4 into 4 intervals. So n is equal to 4. Another thing we're going to figure out, which is super, super helpful here, is going to be the delta t. The delta t is going to be the change in time for each of the intervals. So it's this gap, and this gap, and this gap, and this gap. And the delta t is going to be the same. Delta t, it just makes our math so much easier. So how do we figure out what that delta t is? Well, the end value we're going to call b, and the starting value, which was 0, we're going to call a. So how many intervals did we have there? We had 4 of them. Our delta t value is going to be equal to b minus a over n. So if we decided there are 4 intervals, n is 4, you take the upper value of, in this case, the time, the x coordinate, so 4. So 4 minus 0 over 4 is 1. 4 minus 0 over 4, because n is 4, is 1. We will have delta t values that could be smaller. Now, it also means you could cross multiply this and end up with n is equal to b minus a. So you end up with n, if you cross multiply this, equals just the t and the n switch place. So n is equal to b minus a over delta t. So what that means is if you're given n, you can find delta t, and if you have delta t, you can find n. So how could we be more accurate? Because right now we have a minimum and a maximum of a difference between the two of 160 minus 132. So we have 28 is the difference between our min and our max. 28 is the difference between our min and our max. We love that to be smaller. Well, what we can do in this case is we could just fill in, if we had more data, we have a better idea of a smoother curve. So if you draw this out, we have all these minimums like this, these red rectangles right here. And what we've done is the delta t, instead of being 1, the delta t goes from 0 to 0.5. So the delta t is equal to a half. So the delta t is a half instead of 1. What would the max look like? It would be all the way up to the blue up here. Again, you just have a higher density of rectangles. So what did we do up here to get all these areas? It was the base times the height. The base times the height. So for the red ones, the base for all the red ones, we're going to factor that as a half. What's the height for all of them? Well, it's 20, 26, 30, 35, 38, 42, 44, and 46, ending right there. So you put all those into add it all together. So those are all those red rectangles, and you end up with a minimum of 140 and a half. Now we're going to do the same thing for the blue. The width of each is a half, but now we take all of those right there. So if you do that right there, you end up with a max, and you got to add them all up first. Excuse me, I circled the top instead of the bottom. It's instead of those red ones, it's all of these. So it's 26 to 48. So it's 26 plus 30, all the way up to 48. You end up with a max of 154.5. You know, mixing my forms here. Before it was 132 to 60. Now it's 130. Now it's 140 and a half to 154. So our gap is smaller. We're getting a better and better. We're doing better and better. So right now, the actual is going to be between these two things, 154 and a half and 140 and a half. It's getting smaller. So our range is actually only 14. So instead of 28, we've halved it to 14. So where does that come from? Well, here is a carefully drawn version of what we just did. And here are the gaps at each case, these red rectangles here. Those are the gaps in each case between the upper and lower estimates. And if you slide them over, you end up with this one big rectangle, The top being 48, the last value up here, the bottom being 20, and the bottom, the base having a width of delta t. So in this case, it's the upper value minus the lower value over, and then multiplied by delta t, the 1 right there. Well, what did we do before? What did we do next? We did the same thing, but the delta t in this case was equal to a half. So the upper and lower stayed the same, but the base of this rectangle is now a half. So this area right here is 14. We would love this to go to 0. We'd love it to be really, really, really small between the upper and lower, and we do that by making delta t smaller and smaller. But we need more data to do that, or we need the function that we're modeling. Right now, we're just using tables to add together rectangles and have an upper estimate and a lower estimate.